Assalamu alaikum and good day everyone. I'm your teacher Muhammad Ikram from Pakistan International School, Taif, KSA. Today is our 14th lecture. It is about the interconversion of energy, unit number 6. In today's lecture, I will tell you how energy is converted from one form to another. So let us start with the name of Allah Almighty. Bismillahir Rahmanir Rahim. What is interconversion of energy? In fact, interconversion of energy is the conversion of energy from one form to another form. Energy conversion is also called energy transformation. According to the principle of energy transformation or energy conversion, energy is neither created nor destroyed, but can be transferred from one form to another form. Or energy is transferable to a different location or object, but it cannot be created or destroyed. To explain these principles, let us move on to the next slide. The interconversion of mechanical energy. Usually, our main focus is on the interconversion of mechanical energy. Mechanical energy, is the sum of the kinetic and potential energy of any system. So, the conversion of kinetic energy into potential energy. Let us start. You see the child on the bicycle. He is rising on a slope. As you see, look, in the beginning, he has a kinetic energy. As he rises, his kinetic energy decreases because of the reduction in its speed. So, because why he is rising against the gravity? As you see, at the top of the mountain or this cliff or this slope, you see he has a maximum potential energy, right? So he possesses a maximum potential energy. You see, at this point, he has maximum potential energy, max potential energy, right? But he has what? He has zero kinetic energy. Why his kinetic energy is zero at this point? Because he is not moving. Once he starts a downward motion, then you will notice that he gains kinetic energy. His kinetic energy increases, but at the same time, his potential energy automatically decreases. Why his potential energy automatically decreases? Because potential energy is mgh. So as he comes downward, his height, he lose height. So as he lose height, so his potential energy decreases. So where that energy has gone? Actually, that energy has converted into kinetic energy as he moves. And you know that he has an acceleration. And the kinetic energy equation, if you remember, which is equal to half mv square. So you see that as he moves downward, he gain velocity. His velocity increases and his kinetic energy increases. So the kinetic energy, the potential energy changes into the kinetic energy. When he arrives at the bottom, right at the time of the arrival, he has maximum kinetic energy. So you have seen in the beginning when he was rising, or when she was rising on the clip, you see that he was having a maximum kinetic energy, and as he was rising, his kinetic energy was decreasing, right? Because of this, because of his motion against the gravity, and he gain the potential energy. The work done while rising on the slope was converted into what? Converted into the kinetic energy, the potential energy, right? As he gain height, as the height increases, the potential energy increases. So the loss in the kinetic energy appear in the gain in the potential energy. At the top, at the highest position, he has now the maximum kinetic energy. During his downward journey, his potential energy start decreasing due to decrease in H, and he gains kinetic energy due to increase in velocity. In both the cases, you have seen the mass remain constant, right? And the energy increase or decrease occur. The kinetic energy changes into potential energy and vice versa. The potential energy changes into the kinetic energy. So what we have learned here, that the loss of kinetic energy is in fact the gain of the potential energy. So during the rise, the kinetic energy decreases, and during the downward motion, the potential energy decreases and the kinetic energy increases. Now let us see in this simulation. You see, look, for this car, you see as the rises on the top, the potential energy increases and the kinetic energy decreases. During the lock, during the kinetic potential energy rise, now the potential energy decreases, the kinetic rise. The green represents the kinetic, while the blue represents the potential energy. So you see, during the rise, the potential energy increase. During the fall, the potential energy decreases and the kinetic energy increases. But the total energy of the system remain the same. Why? Because you see that if you notice the rise in the potential energy, at the same time you notice decrease in the kinetic energy. So the sum of the energy, that is the sum of this energy, we call the total energy. This total energy is the sum of the kinetic energy plus potential energy, and this remain the same. This is constant. So from this, we have learned that the total energy of the system remain constant, as you see. Why? Because during the rise and fall, the system has partial kinetic and partial potential, but the total energy of the system remain the same. Whatever the energy you have in the beginning, you have the same energy in the end for the mechanical system. If we consider the system as an isolated system, this is for an isolated system, remember. Now, what is isolated system? Isolated system is the system in which energy can neither enter nor leave. We only consider the changes of energy from kinetic to potential, right? We ignore other kind of changes like changes into sound, changes into heat during friction, right? We ignore those. Why? Because for our this kind of system, those energy loss or energy changes are very minute and small, and we ignore them. So that kind of system we consider as an isolated system or a closed system where energy cannot enter or leave from outside. So if the system is isolated, the total energy of the system remain constant. We call this is the law of conservation of energy. This is one of the uh, fundamental law of physics, just like the law of conservation of mass. As you have seen, that during the motion, the mass of the system remain constant. So in the same way, the physical quantity, which we call the total energy, remember, I don't say kinetic or potential alone. I say the total energy. The total energy of the system always remain constant. That is another physical quantity, and this is one of the most useful quantity in the in a physics. We use this law of conservation of energy for various systems to calculate velocities, to calculate masses in a simple way. So in this slide, you have learned about the energy transformation, law of conservation of energy, and there is the decrease in kinetic energy, in fact, the increase in the potential energy. These few important points like energy transfer, energy transformation, law of conservation of energy, these are extremely important. Now, what is energy transfer? Energy transfer is in fact the movement of energy from one location to another. You see, look at the bottom, you have the maximum kinetic energy, right? And from the bottom, you have transferred this energy to the top, right? This is known as the energy transfer. In this energy transfer take place with the help of work done. So if you remember my very first lecture where I told you that work done is in fact the method of transfer of energy. So you have seen that energy is transferred from the bottom to the top of the clip. This energy transfer take place with the help of work done. By this way, with the help of this work done, we transfer energy from one location into another. Similarly, the same happens when the cyclist moves from the top to the bottom. The energy transformation. Energy transformation is a term which we apply to energy changes from one type to another. You have seen energy transformation. Why? Because the kinetic energy of the cyclist changes to the potential energy of the cyclist when he arrives at the top of the cliff. The law of conservation of energy, I already told you that energy is neither created nor destroyed, but it can be changed from one form into another form. Throughout this journey uh, the from this point to this point, you have seen that kinetic energy change into potential energy, and then potential energy change into kinetic energy. During this process, the total energy of the system remain constant. What we have learned from this, that whenever there is decrease for any mechanical system, the whenever there is decrease in the kinetic energy, it will be increase in the potential energy. Energy will go nowhere. Let us move to the next slide. Law of conservation of energy for the various system. As I told you that energy is neither created nor destroyed, but can be changed from one form into another. However, the total energy of the system always remain constant. You see the food we eat changes into the has the sorry the let us just go back for into the previous system. You have seen that the cyclist was having a mechanical energy system. In the beginning, the cyclist was having kinetic energy. Where the cyclist has got the kinetic energy from? Look, before rising, before moving, before cycling, he was having potential energy stored in his muscle. From where did he get this potential energy? Of course, from the food he has eaten. And for example, look at the apple. It has a chemical energy stored in it. That chemical energy transferred to this the cyclist, right? So that is the energy transfer, energy transformation, and the cyclist has now a kinetic energy. There is another example. Look, for example, the torch. How the torch gives us light? Because there is cell in it. The cell has a chemical energy. That chemical energy changes into light energy, and the total energy of the system remain the same also. Why? Because when you switch on the torch, the energy stored in the cell or battery decreases, and the energy in the torch which you give the light energy, that is increases. Similarly, the electric lamp, you see that there is electric light, the electrical energy, that electrical energy changes into light energy. So energy transformation and energy transfer take place, but the total energy always remain the same. Look for the transportation system. This is so You see the chemical energy stored in petroleum, diesel, or gasoline. That changes into what? That changes into the kinetic energy of the car. Similarly, the light energy of the sun, they changes into chemical energy. This transformation take place because of the photosynthesis process. So there, look at in this case, that is electrical energy changes into heat energy for the toaster. So that is how the energy transfer take place, and it is based on the law of conservation of energy. The energy conservation, look, not all of the energy are in fact used in some useful work done or whatever actually we are interested or whatever we wish and desire to get from. For example, if you have some energy sources, let us, you see, for example, if you have some sources of energy, right now that is, look at this system here. You have the chemical energy. You have the chemical energy stored like in the wakes here. That chemical energy changes into light energy. From the candle, we expect light but not heat. So you see, like from the candle, look, as it burns, then the chemical energy changes into light energy. This burning takes place in the presence of oxygen. But you see, we only get some of the useful light and we get some of the energy loss. The energy loss, it is in the form of what? It is in the form of heat, right? And what we actually need is light, and we get some of light energy and some of heat energy. But for the candle, most of the energy is in the form of heat. For example, look, this is not what based on facts, but it is just what my assumption, you may say. We may get round about 30% or less light, and the 70% of energy is wasted in the form of heat. So that is in the form of what? In the form of heat. So not all of the energy is in fact used in useful work done. Some of the energy lasts. So this is not a pure kind of mechanical system. Here the energy loss take place, and we cannot call this system as completely closed system. Why? Because there is an energy loss. Heat is undesirable and unwanted in this case. For example, if we have a candle dinner at that time, we don't want heat, rather we only want light. So that is how some of the energy is wasted. Let us move on to our next example. The flow diagram of the energy converter. That how the flow diagram is, we will look to all the possibilities and impossibilities for our system when we are going to design such system. For example, our first system is the electric lamp. Here you see an incandescent lamp which uses electrical energy. So you have the electrical energy. My God, it has gone. Let me explain it to you in this system. Let us come back to this again. As you see, that we have all the electrical energy, and this electrical energy is provided by our source. That source is power station. So we get electrical energy from for the power station, and we want light energy in our house. So how this happens? You see, we have the electric lamp, as you see. So as the electrical energy arrives, it is in the form of kinetic energy, right? The kinetic energy, that is, if you see, look at this here, that is as the electron moves to the filament of the lamp here. So every time when the electron pass through the filament of the plane, they have the kinetic energy. So there is a work done, energy transfer take place, and that energy is converted into what? Into light, as you see, light and heat energy. So this is heat, and here you see the yellow is light, the white you may consider as heat. So you see that the energy transformation take place from one kind of electrical energy. We get two kind of energies, the heat energy and the light energy. But for from the electric lane, our sole purpose is light energy. So where the rest of the energy goes, so our output is, that is the input electrical energy, and our output is the light energy, which is desirable, which is what we want. And the energy, that is the heat energy, which is unwanted and undesirable, which we don't want. This is why nowadays you may see you may see that most of the light bulbs are replaced by the energy saver. Why? Because they this is 80% heat, and the lamp only give you 20% light, and for this I am pretty sure that this happens. So how much of your input energy is wasted? This is what wasted. This is what we don't want it. So that is the energy conservation in the electric lamp, but the total energy of the system always remain constant. This is what I will be telling to you. For example, you have this light energy and you have this heat energy. So what is the total energy? The total energy is the sum of the heat energy plus the sum of the energy light energy. So you see the heat energy is 80% and the light energy is 20%. So what you get is 100%. That is your total energy, and that total energy is your electrical energy. That is what I'm discussing, the input at your house. When it arrives at your house, I consider it as 100%. At the power station, it is a different story. There will be also loss. I'm not discussing that thing. Okay. So that is this one. Now let us move on to the next slide. Here you see the oh my god, I misplaced. This is so uh, it is this is I'm so sorry. This is not the vehicle running with a constant speed on the level road. Look, I just not, this is not okay. I'm so sorry for this mistake. It is the that is the mm, that diagram is not rightly placed. So this system is, in fact, it is, you see, this is matching to the flow diagram, but this power generation diagram, it is not for this, not related to this topic. I'm very sorry for this. I have to show you another simulation regarding to this, but let me explain it. For example, you can generate the power by two ways. That is for the vehicle, that may be electric vehicle, and that may be the one fueled by chemical energy. So we talk the one fueled by chemical energy, maximum or major transportation 95%, I would like to tell is powered by chemical energy. So you see, you have the chemical energy, and that is the first thing is the your car engine ignition of the fuel causes heat energy, right? So first you have the oil, that is which have the chemical energy stored in it. That chemical energy much, it is generated into heat. So heat output, this is also our output, right? That is also the output. This is our useful work done. This is what we require. We do not require this and we do not require this. So when the vehicle is moving, you see the motion of the vehicle. The vehicle has a kinetic energy. That kinetic energy you gain from the chemical energy stored in the fuel, which is oil, petroleum, gasoline, or whatsoever you call it. And then some of the energy is maximum of the energy is wasted. That is the heat. That is in the form of what? That is in the form of heat energy. That is wasted, right? So heat energy, when the car engine is running and when you place your hand on the bonnet of the car, so it is too hot, right? When you touch the tire of the car, don't do that, it is risky. So when you touch it, once the car stops, it is too hot. So maximum of the energy is utilized, is wasted into heat energy. Very less energy. I would like to be around about 30 to 40% of energy is changes into useful work done. That is the kinetic energy, and that is what we want. And much of the energy is wasted in sound energy, and that is how you hear a nice and a very dense populated area. That is the sound energy, or in a dense populated traffic. So that energy is wasted in the form of noise, sound energy, and you hear this sound of the energy, the sound of the vehicle when its engine is running. So the only energy which is utilized in this case is 30 to 40%, but still this is best. Why? Because that we need transportation, right? So sometimes we will compromise. And how? What we compromise? We compromise maximum energy loss, right? Over what? Over the kinetic energy gain. Why? Because we need to travel faster, right, than our normal rhythm. So this is the second example of the vehicle running with a constant speed on a smooth level road, right? That is the end of our today lecture. So thank you all for being with us.